Good afternoon, class. We are looking at exam 4 review. Chapter 4, application of differentiations. Chapter 5, integrals. And now the third part covering 5.2 to 5.3. Section 5.2, the definite integral. 5.3, the fundamental theorem of calculus, short FTC. Five point two, the definite integral. Suppose a continuous function f is defined on the interval of a to b, a closed interval. The interval is divided into n subintervals. Delta x is b minus a over n, and x sub 0 is a, x sub 1 is equals to a plus delta x, all the way to x sub n, which is a plus n delta x, which is b. A Riemann sum associated with f is the following sum. The integral of a to b f of x dx, by definition, is equal to the limit as n goes to infinity of summation of I going from 1 to n of f of x sub I delta x, which this part is f of x sub 1 delta x all the way to f of x sub n delta x. And again, you take the limit of that. Take a limit of that. Delta x, b minus a over n, x sub I is a plus I delta x, where x sub I is any point chosen in the interval. Let y equals f of x be a continuous and non-negative function over an interval of a to b. Definite integral, which is a number, is the limit as n goes to infinity, equivalently as delta x goes to 0, of the Riemann sum of the areas of rectangles under the graph of y equals f of x over the closed interval of a to b. So the area has this precise definition. A is the limit as n goes to infinity of summation of I going from 1 to n of f of x sub I delta x. Delta x is b minus a over n, x sub I equals a plus I delta x. This represents an area under the curve if the function is non-negative. Otherwise, it's the difference of areas. And that's important to understand. Now, let's look at a definite integral, which is a number. Let's look at every part. Integration symbol, the elongated S. The symbol was introduced by Leibniz, and it's called an integral sign. It is an elongated S and was chosen because an integral is the limit of sums. So that's pretty clear, everybody. Lower limit of integration, upper limit of integration. Integrand, variable of integration, also known as dummy variable, because it has no effect on whether you use, when we want to calculate this, which is a number class. Remember that this is a number. It doesn't matter if we have x or t or any other variable. Makes no difference. It results in the same thing. It is called a dummy variable because the answer does not depend on the variable chosen. The dx simply indicates that the independent variable must be x. The integral of a to b f of x dx is a number. It does not depend on x. We could use any letter in place of x without changing the value of the integral. For example, the integral of a to b f of t dt. These two must be the same. or its approximation. The integral of a to b f of x dx is approximated by the Riemann summation of f of x of I delta x as I goes from 1 to n, which is this one. The sum is called a Riemann sum. Precise value is when we take the limit of that and we let n go to infinity. The limit of the summation I going from 1 to n of f of x of I delta x as n goes to infinity. This is the precise answer. Express as an integral on the interval of 0 to pi, this Riemann sum, and reminding everyone of a couple of things. Number one, the integral of a to b f of x dx is the same as the limit of f of x of I delta x as I goes from 1 to n. Take the limit, let n go to infinity. The area under the curve is precisely that limit. So let's put them next to each other. And so what do we notice? This must be this. As far as a and b, I hope everybody can see that for this integral a to b, it's 0 to pi, it's given. It's the interval. So the lower limit is 0, the upper limit is pi. We got to figure this out. If this is f of x of I, f of x must be what? X cubed plus x sine x. A is 0, b is pi. Put it into the integral format. The integral of a to b becomes the integral of 0 to pi. F of x is this function, dx. So this limit, everybody, that we have here is equal to the integral of 0 to pi, x cubed, x plus x sine x dx. So noticing what it means to be, okay? Expressed as an integral, the limit as n approaches infinity of summation I going from 1 to n of sine of 2 pi I over n times 2 pi over n on the interval of 0 to 2 pi. The difference between this and the other one is that delta x is given here, okay? The other one was just delta x, and of course you change it to dx. We will do the same thing. We change it to dx here, okay? But the purpose of that is to help us see the a to b. That's why we have this one. A to b is given. All right, so we're going to do the comparison again. We're going to do the comparison. So delta x is b minus a over n. A is 0. B is 2 pi. So delta x is 2 pi minus 0. Delta x is b minus a over n, everybody. 2 pi minus 0 over n, or simply 2 pi over n. So we got delta x. X sub I is a plus I delta x. So x sub I is a, which is 0 plus I times this. So a is 0, has no bearing. I times delta x, so 2 pi I over n. Therefore, if we look at this one, we see the delta x, everybody, of course, as expected. Let me use this color. So this one obviously is this one. Now, f of x sub I is sine of 2 pi I over n. F of x sub I is sine of 2 pi I over n. So what should f of x be? Since we found x sub I, then f of x must be sine x, same interval 0 to 2 pi. This is x sub I, everybody. So what's the function? The function is the integral of a to b f of x dx, the integral of 0 to 2 pi sine x dx, the integral of sine x dx. Use summation formulas to compute the integral of 0 to 2, 1 minus x squared dx. And of course, reminding everyone that this definite integral, which is a number, uses the Riemann sum as follows. So previously, we were trying to just see how we arrive at f of x. Going back and forth from this format to this format, from this format to that format. That's what we did before. Now we actually work it out. To work it out, the area under the curve is defined as this limit, everybody. Later on, we'll find an easier way, by the way. But for now, just like we did the definition of a differentiation, now in essence, this is definition of integration for definite integral. So we're going to use that. And delta x is this, x sub I is that. And the following, I'm going to remind you some of the stuff you should have seen. The summation of 1 is n if I goes from 1 to n. The summation of c is a number, is a constant, nc if I goes from 1 to n. The summation of I is n times n plus 1 over 2 if I goes from 1 to n. The summation of I squared is n times n plus 1 times 2n plus 1 over 6 if I goes from 1 to n. And the summation of I cubed is in essence the square root of that, n squared times n plus 1 squared over 4 if I goes from 1 to n. And we're going to use that. So we are going to follow this using the fact that the function, everybody, is 1 minus x squared, and the limits a is 0, b is 2. So f of x is 1 minus x squared, and a is 0, b is 2. Just reading this. We are reading this one, everybody. That's all we are doing so far. Delta x is b minus a over n, 2 minus 0 over n. X sub I is a plus I delta x. So simply, since a is 0, 2 over n times I, or 2I over n, however you want to write that. So that's x sub I, a plus I delta x results in 2I over n, or 2 over n times I. And so from here, we're going to go here. We're going to write this one. We're going to write this summation, and then we're going to apply the limit. We can apply the limit at the end. So for now, to make it a tad easier, let's just find this. When we simplify, then we take the limit. So that's one way to do it, everybody. So summation of f of x sub I delta x is the summation of, if this is f of x, if this is f of x, what is f of x sub I? 1 minus x sub I is 2I over n quantity squared times delta x 2 over n. So we are going to show this part. Okay, everybody? One more time. F of x sub I. Here's 1 minus x squared. So replace the x with x sub I. Just 2I over n. So 1 minus 2I over n squared times 2 over n. All right. So we are going to work on this, simplify it, and see what happens here. This one is 4I squared over n squared. We are going to distribute over here. We get 2 over n. When we multiply it by 1, when we multiply it by the second piece, we get 8I squared over n cubed. Now, we are going to look at this one. As I goes from 1 to n, so we can take the 2 over n out here and 8 over n cubed out, and we cut it into two pieces, two summations. Okay, everybody? You cannot take the I out because the summation applies to I. As you see, summation of 1, we can replace it with n. So this, we can replace it with this. And I squared, we can replace it with this. Right? So let's do that. So we are going to write 2 over n times this, which is n, 8 over n cubed times this, which is n times n plus 1, times 2n plus 1 over 6. When we simplify this, first and foremost, this drops and I get 2. Now, I want you to see what happens here. So I want you to look at the numerator. The numerator, everybody, because we're going to take the limit. I hope you see that 8 and n and n and 2n, the product is 16n cubed. I just want the first term. The rest of it will not be important. You'll see in a second why. Although this is an easy product, you can do that. But 8 times n times n times 2n is 16n cubed, and the bottom is 6n cubed. What happens with the rest of them, the reason I say they are not important, because we want to take the limit of this expression, okay? So this integral is the limit of this expression. Now we are going to apply the limit. And when you want to apply the limit, as you recall, one easy way, the degree of the numerator is 3, the bottom is 3. So this part is minus 16 over 6. Remember the horizontal asymptote. So 2, you're taking the limit and let n go to infinity. 2 doesn't matter. The constant remains unchanged. Minus 16 over 6. And 8/3. 2 is 6/3. Their difference is negative 2/3. So we evaluated this expression accordingly. So it's very straightforward. I hope everybody is fine with that. So part A, question example 4, to evaluate the Riemann sum for this function f of x equals x cubed minus 6x, taking a sample points to the right endpoints. To be the right endpoints, A is 0, B is 3, and n is 6. So we're going to use the right endpoints to evaluate this. I'll show you how to do that. We've done this before for the right endpoints, left endpoints, and the midpoint. We've done that. And then they want us to evaluate this. This one is what we just did in the previous example that requires the limits. And we're going to do that. But just to remind you of this part in essence, because the area under the curve is Rough estimate using that. Okay, and it depends what's n. The larger the n, the better the approximation. I hope you remember that. So here's the function, assuming everybody can easily craft this. Okay, y or f of x equals x cubed minus 6x. And here's the graph, and we want to go from a equals 0, the y-axis, to b equals 3, the vertical line 3. So we are interested in the area under the curve, this area and this area. Because this portion is above, is considered positive, this is negative. So when you're done with this, you get the difference of areas. Okay, you get the difference of areas, and it's important to understand everybody. So f of x is x cubed minus 6x. A is 0, b is 3, n equals 6. We can calculate the delta x as b minus a over n. B minus a over n, and that's 3 minus 0 over 6 is 1/2. And remember what I told you, if you want to easily calculate this, just we are going to go from A to B, draw a you know, line segment from A equals 0 to B equals 3. And since this is 1/2 of 0.5, so just add 0.5 and then 1, 1 point. So you have 1, 2, 3, 4, 5, 6 subintervals. Now, we are going to use the right endpoints, the left endpoints, or the midpoints. More specifically, they ask for the right endpoints, which means you don't need this one. You use this one. You use all of them except the first one. For the left endpoints, you use all of them except the last one. And for the midpoint, you just, over here is 0.25, and then 0.75 and so forth. You remember that. So we want R sub 6, which is going to use delta x times f of x of 1, f of x of 2, and so forth. So we are going to multiply 1/2 but by f of 0.5 plus f of 1, f of 1.5, all the way to 3. And these are the subintervals and therefore rectangles. We are using the right endpoint. See this one, this one, this one, this one, and then this one, and this one. This, as far as the graph is concerned, those are the right endpoints. Let me see what color I can use here too. We are using those. Now, you have to put it back into the original function. Here's the function, everybody. Let me just make sure we understand how this thing is going to work. Let me, this color. So you're going to put this into this function. So you're going to put 0.5. So 0.5 cubed minus 6 times 0.5. So that would be 0.125, just as an example. If you put 0.5 into the function, you get 0.5 cubed minus 6 times 0.5, just to give you an idea. 0.5 cubed is 0.125. That one is minus 3. You get 2.875. It's just as an example. If you plug in 1, you get 1 minus 6, negative 5. If you plug in 1.5, you calculate it and so forth. And everything adds up and you multiply by delta x, which is 1/2, you get negative 3.9375. The number of decimals, if they don't mention it, you want to carry a lot of decimals. I want you to know that. And of course, note this value represents the difference of areas. That's why it's negative. Notice this area is larger than this area. Okay? So difference of areas. Why difference of areas? Because the function is not positive from 0 to 3. Portion of it is positive, portion of it is negative. That's why. So that's a Riemann zone. But what about part B? So we're going to continue working on that. Part B, we want to evaluate this, which means we are going to find the delta x. But delta x is no longer b minus a divided by the n, which was 6, but rather n in general. Okay. And reminding everyone that it's the same function, but this time you find the exact answer. Exact answer. So we write the function, we write a, we write b. We are going to calculate delta x is b minus a over n, which is 3 minus 0 over n. X of I is a plus I delta x, 0 plus 3 times I over n, or I times 3 over n, either way. All right, so this integral is equal to the limit now. And so what we are going to do, we are going to look at this part and evaluate this one again. Later on, we will look at this indefinite integral and the easy way out, which you find the antiderivative and you plug in. But for now, and I'll discuss it in the next page, but the easy way is coming up, okay? For this one, we are going to write f of x of I times delta x. So here's f of x. We are going to put 3i over n, so we get 3i over n. So f of 3i over n times delta x, which is 3 over n, okay? Now, we want to take this limit, and what we can do, we can for now ignore the limit and simplify this part, everybody. Let's work on this. And then last, whenever it's completely simplified, then we take the limit, okay? We can do that. So what happens next? It's very simple. We are going to work on this part, and to do so, we are going to write x cubed, which means 3i over n to the third, minus 6x, minus 6 times 3i over n, and this 3 over n remains somewhere. You can put it in or outside the summation sign. See, notice the limit is not there. I'm going to apply the limit at the end, so you don't want to, worry about that. Now, this one is 27. I cubed over n cubed. This one is minus 18. I over n. And you can separate the I. Everything can come out of the summation sign. What remains in there, anything involving n. So with that being the case, we have these two, AD1, these two, n to the power of 4 I cubed remains. And then 3 times 18, 54. N times n is n squared. So minus 54 over n squared remains summation of I. So notice what we do. So this I cubed remains, this I remains. So take a look. Make sure you see what remains and what comes out and why. The reason we can take out the 81 over n to the power of 4 or 54 over n squared, because the summation applies to I. It is I that goes from 1 to n. Okay, so we want to make sure we understand that. All right. Now, we are going to replace the I cubed, everybody. I'm going to replace the I cubed with n squared times n plus 1 quantity squared divided by 4. And we're going to replace the I, by that I mean summation of I, with n times n plus 1 divided by 2. Now we're going to simplify this as follows. This one class, please understand this is n squared, this is n squared, so it's 81 n to the power of 4, this is 4 n to the power of 4. The very first term is 81 n to the power of 4, and the rest have smaller exponent for n. This one, 54 n squared, and the rest of them have smaller exponent. So the limit, this integral, is the limit of this expression. Because n is to the power of 4 and n is to the power of 4, they have the same degree. This becomes 81 over 4 minus, this has degree 2 minus 54 halves. And we get the common factor of 4. AD1 minus 108 is minus 27 over 4. This is the exact answer, everybody. This is the exact answer. Let's move on, and we are going to continue with this concept of evaluating the integrals using signed areas. Use the signed area of interpretation of the definite integral to compute the integral of x dx from -1 to 2. The function y or f of x is x. A to b is from -1 to 2. A is -1, b is 2. If you were to graph this function y equals x is a line that goes through the origin. We want to go from -1 to +2. That means we want these two areas. This part is above. This portion is positive. This portion is below. the x-axis. So therefore, it's the difference of the area. So you calculate this area, you calculate this area, the difference is the answer. And obviously, it clearly this is larger than this one, so it ends up being positive, but nevertheless, it's the difference of the areas. So how do you calculate the area? You're going to use area equals 1/2 base times the height because the geometric shape that you are familiar with, and this point has coordinates 2, 2. This one has coordinates -1, let me just do this one more time. -1, -1. So going back to this one, remember this is a right triangle. The legs are, one of them is the base, one of them is the height. So 1/2 of 2 times 2, that would be the area of the right of the green triangle, the area of the red triangle, half of the base and the height. The distance is 1 here. Okay, so 1/2 of 1 times 1, which makes it 1/2. So what is this? Is the difference between the two. 2 minus 1/2, which is 3/2. Okay. Now, we will use the easy way out later on, but this is just to get us started, everybody. So what is the easy way out? The integral of a to b f of x dx is capital F of b minus f of a. That means uh, find the antiderivative and plug in the limits. So as you know, the antiderivative of x is 1/2 x squared. We are going to put -1 and 2 in there. So 1/2, you put 2 squared, you get 4. -1 quantity squared, you get +1. So the difference of the two, that's why f of b minus f of a. So 1/2, you plug in 2, you get 4. When you plug in -1, you get 1. The difference is 3, and it's 3/2. And this is exactly what we got here. Now, the purpose of this one is to verify that the areas work, the antiderivatives, and the definite integral methodology f of b minus f of a works. And so there is no reason to do the limit. Ultimately, this is the easy way out. Of course, we should know how to do the limit. So the geometry was familiar, we could calculate the area. But remember, when the geometry is not familiar, you either have to use the limit or this one. For now, if they ask you to use the limit, you have to do so. Here's what I want you to try later on using, you want to graph the function. The function is 6x. And then use the signed areas to show that this is equal to -45. It's a good practice, everybody. All right. This question, we want to use geometry to evaluate this. And that means you should know analytic geometry and the function that is square root of 9 minus x squared from -3 to 3 must be evaluated. So we need to know what type of a function we have. Reminding everybody that when you're dealing with circles, centered at 0, 0, x squared plus y squared equals r squared. Centered at h and k, x minus h quantity squared plus y minus k quantity squared equals r squared. Okay. And of course, the area is pi r squared. The circumference is 2 pi r. So what has it got to do with this function? Well, reminding you about the semicircles in the following manner. If you call this y, if you square it, you get, let me square this first. If I square this, I get y squared. And square this, I get 9 minus x squared. And that means this is a semicircle, and it's the top, it's the graph is a semicircle with the radius being square root of 9, square root of 9 or 3, because 9 is 3 square root. So this is a circle with centered at 0, 0 with the radius 3. This is a semicircle of the same circle. Remember, the top half is the positive square root. The bottom half is the negative square root. The right half is the positive square root of 9 minus y squared. The left half is the negative of that. So we are looking at the graph of G, which is a semicircle of radius 3. And if the area is pi r squared, for this one must be half of that. So half of pi r squared, and r is 3. 9 pi divided by 2. The second method, and you can't use that, is discussed using trigonometry in calculus 2. Otherwise, you don't know how to come up with that. Okay. There is a way to evaluate that using trigonometry. Again, in calculus 2. All right. Now, properties of definite integrals. Let f and g be continuous functions over some interval of a to b. Definite integral at a point a, if we integrate from a to a, f of x dx becomes 0, because delta x becomes 0. Delta x is b minus a. B minus a becomes 0. If the lower limit and upper limit is the same, this definite integral, which represents a number, becomes 0. Okay. So, or if you look at the concept of a curve, a point does not cover any area, remember, because a line or line segment is its thickness is 0. Sum and difference rules. The integral of a to b f of x plus minus g of x dx, as we go from a to b, we can cut them into two pieces. So, for example, if this is y equals f of x, this is g of x, the area under the curve under f of x is this, under g of x is this entire thing. We will add them up. That can be shown with a graph. Scalar rule. If the integral of a to b c f of x dx is of interest to us, we can just evaluate the integral of a to b f of x dx and multiply it by c. So this is f of x. This is 2 times f of x, for example. Dominance. If f is larger than g from a to b, then the integral of a to b f of x dx must be larger than or equal to f integral of a to b g of x dx. So think about this. G is below the f function all the time, which means it's smaller than that. So the area that the g covers is smaller than the area that f covers. Bounding, max minus min. If f of x is between lowercase m and uppercase m, as we go from a to b, then if we multiply everything by b minus a, this one by b minus a, and this one by b minus a, is the same as integrating this from a to b f of x dx, and it must be in between also. So take a look. The idea is this. We're going to evaluate the integral from a to b of f of x dx. So it's blue part plus the green part, by the way. Now, because m is smaller than that, it's the minimum of the function in essence. So it's the width, or you can say the height times the width, which is b minus a. The green area is less than that. And for the maximum, you calculate this. The product of this width, which is b minus a, times this height, which is the maximum, m. Splitting or additivity, additivity. The integral of a to c is the same as the integral of a to b plus b to c, f of x dx, when we split them into two parts. So we want to evaluate the integral of a to c. You can evaluate it from a to b and then from b to c and add them up. That's the idea. Opposite rule, the integral of a to b f of x dx is minus the integral of b to a f of x dx, because delta x will become negative now if b minus a over n is positive. So constant rule, the integral of a to b c dx, you just multiply the c. So if this is b minus a, it comes out as c times b minus a. And non-negativity, if f is positive, as we go from a to b, then the integral of a to b f of x dx has to be positive. And that represents the area under the curve if it's positive. All right, let's look at a couple of examples. Given that the integral of 1 to 3 f of x dx is 6, 3 to 7 is 9, 1 to 3 is minus 4, we want to evaluate the following. What is the integral of 1 to 3 f of x dx? Okay. Well, because of this 3, we get the same thing times 3. So the integral of 1 to 3, 3 f of x dx is 3 times that. So you take the 3 out, and you multiply it by number 6. The answer is 80. What about this? We cut them into two pieces. The integral of 1 to 3, 2f of x minus 4g of x dx. We are going to take the 2 out, we're going to take the negative 4 out, and we're going to write 2 times the integral of 1 to 3 f of x dx minus 4 the integral of 1 to 3 g of x dx. This one is 6. We're going to replace it with 6, so 2 times 6. This one is negative 4, so minus 4 times negative 4. And of course, 12 plus 16. 28. What about the integral of 1 to 7 f of x dx? We notice this is 1 to 3, this is 3 to 7. And we can say, as long as these two numbers are the same, and they are, we can say the integral of 1 to 3 f of x dx and the integral of 3 to 7 f of x dx, they add up. So the answer is 6 and 9, 15. What about the integral of 3 to 1 f of x dx? It's the same as this one, flip it over, therefore it becomes negative. So the answer is 6. This makes it negative. Okay? Very straightforward, everybody. So the fundamental theorem of calculus says the fundamental theorem of calculus is appropriately named because it establishes a connection between the two branches of calculus, differential calculus and integral calculus. It gives the precise inverse relationship between the derivative and the integral. The derivative of a to x f of t dt is equal to f of x. This means if you integrate and then differentiate them onto each other, they give us the function back. Notice. These two must be the same, everybody. Any variable will do. And this one is a number. And this upper limit is this. So this must be the same as this one. And this must be the same as this one. And because we are differentiating, that lower limit a has no bearing. It's a number, it becomes 0. So the fundamental theorem of calculus. Suppose f is continuous on a to b. If g of x is the integral of a to x f of t dt, then g prime is f of x. That's really the same thing in the concept. The integral of a to b f of x dx is capital F of b minus capital F of a, where capital F prime is f. This is the fundamental theorem that we were just discussing, that if you want to evaluate this definite integral, you can go with the limit, okay, or the easy way out, capital F of a minus f of a. And one of them is called FTC1, one of them is called FTC2, Fundamental Theorem of Calculus 1 and 2. It depends on the text. I don't want to dwell on that. There are two of them. So again, the integral of a to b, lowercase f of x dx, is f of b minus f of a. The derivative of a to x f of t dt is f of x. And this is the limit that we have discussed. Again, to find this, we can go by the limit, or we can go by this FTC, which makes life easier. Let's look at a couple of simple examples to make some sense out of this. So if I want to evaluate this, I don't want to go with the long way, which is the limit. Rather, I want to go with the easy way. So first and foremost, x to the power of 7, the antiderivative is 1 over 8 x to the power of 8, and I don't need a constant. Okay. The reason I don't, because I'm evaluating, I plug in 1, I plug in 0. 1 to the power of 8 is 1, 0 to the power of 8 is 0, so I get 1 over 8. I don't need a constant because it makes no difference. Tip: even if we use another antiderivative, that means capital F of x plus c, if we put plus a constant, in the evaluation theorem, the result will be the same, because capital F of b plus c minus capital F of a plus c, those c's cancel each other. That's why for this one that results in some number, we don't do that. Okay, everybody? What about this one? As you know, x to the power of negative 1 is the same as 1 over x, so this results in natural log. And we keep the absolute value. I want to make a point. The absolute value over here makes no difference. You plug in 2 and 1, and ln1 is 0, so you get ln2, and you keep it as ln2 because it's an exact answer. However, what happens here, we're looking at the same question, the limits have changed. Now, again, so far the same, but now we do keep the absolute value, because in part B, if you lose the absolute value, it's fine, but in this part, it's not. Because if you lose the absolute value, ln of negative 1 is undefined. We don't have anything like that. So this is ln of 1 minus ln of 2. ln of 1 is 0. So you get minus ln2, a precise answer, everybody. Okay? Precise answer. How about the integral of 0 to pi sine x dx? You recall the derivative of sine is cosine. The integral is negative cosine. So negative cosine, we don't need a constant because it's going to be a number. We plug in pi and 0. So I'm going to keep the negative out, and I'm going to say minus, and then cosine pi minus cosine of 0. As you know, a cosine pi is negative 1. Cosine 0 is positive 1. So you get minus 2 here. This negative makes it positive 2. Very straightforward. Gotta get a couple of questions. We've already done these integrations. We just didn't do the uh, definite integral. So I hope you remember that this one, for example, remember the independent variable is t, so it's t plus sine t, because the derivative of cosine is negative, but the integral is positive sine. Okay, I hope you remember we did this. So plug in power 2, you get power 2 plus sine of power 2 minus plug in 0. So sine of power 2 is 1, sine of 0 is 0. So simply you get power 2 plus 1, which is exact. To do this, we are going to change this to x to the power 1 half. And this is 1. So 1 and 1 half becomes 5, x to the power of 3 halves. Okay, so square root of x is changed. The reason we do that, so it gets ready for the power rule, everybody. So this one is 5 over 3 halves plus 1 x to the power of 3 halves plus 1. This one is 3 over 1 half plus 1 x to the power of 1 half plus 1. And both cases, we're going to evaluate from 1 to 4. This is 5 halves. So this is 2, 3 halves. This is also 2. Now we're going to plug in 4 and 1. We want to evaluate this. So 4 to the power of 5 halves is the same as square root of 4 to the power of 5, which is 2 to the power of 5, which is 32. This is square root of 4 to the third, which is 2 to the third, which is 8. So 2 times 32 is 62, plus 2 times 8 is 16. 1 is 1 no matter what, to the power of 5 halves or 3 halves. So you're looking at 2 and 2 is 4. So minus 4. The answer is 76. Put 64 here. I mentioned 64, but I put 62. It's 2 times 32, 64. Evaluate the integral where f of x is defined as 2 when it's between negative 2 and 0, 4 minus x squared, when it's between 0 and 2. Because we want minus 2 to 2, please understand that we are going to cut it into two pieces. The integral from negative 2 to 0 is going to use this part, this function, this piece is a piecewise defined function. For the second leg from 0 to 2, it's going to use 4 minus x squared. By the way, if for any reason, instead of minus 2 to 0, we had minus 8 infinity to 0, we would use the same thing because of the limitations given here. The same thing if it were 0 to infinity. I just wanted to see that, everyone. Okay. And so you're going to evaluate this. You get 2x from negative 2 to 0. This one you get 4x minus 1/3 x cubed from 0 to 2. So those should be easy evaluation. Okay. So plug in 0 and then plug in negative 2, plug in 2 and then 0. So the first part, 2x going from negative 2 to 0. When you plug in 0, you get 0. So this is 0. We don't have to worry about it. So plus 4. This one is 8. Use a different color. This one is 4 times 2, 8, minus 2 cubed, 8 thirds. Never mind, this one is 0. So you have 4 and 8 and negative 8 thirds. 12 is 36 thirds, minus 8 thirds is 28 thirds. Find the derivative of the function g of x is the integral of 0 to x, the square root of 1 plus t squared dt. We want to find the derivative of this function. F of t is the square root of 1 plus t squared, which is a continuous function. The reason why, because square root, remember, the domain is what's underneath must be larger than or equal to 0. If you remember that, here's the reason. 1 plus t squared greater than or equal to 0, and it's all real numbers because of the fact that it's 1 plus t squared. That's why. So by FTC, what is the derivative? Just replace the t with x. So the derivative of the integral of a to x f of t dt is f of x. So g prime, because we want the derivative, is the same function, replace the t with x, square root of 1 plus x squared. Differentiation and integration onto each other. What about this one? The derivative d dx is what we want. Of the integral of 1 to x squared sine t dt, and of course the function is sine t. F of t is sine t. The derivative of a to g of x. Now over here we had x. Now we have a function of that by the chain rule of f of t dt is f of g of x times g prime of x. This is by the chain rule, everybody. One more time. The integral of a to x f of t dt is just f of x. Replace the t with x. If it's something other than that, it's a function of x. So again, replace the t with x. In this case, replace the t with g of x. And then g prime is by the chain rule. So with that being the case, sine of x squared times the derivative of x squared, which is 2x. And normally we write that in front. So 2x sine of x. Let's look at it differently. I want to show you that is interesting. If you integrate, if you look at this one, because it's doable and sometimes it's not, this one, just integrate this one, integrate sine, and then evaluate it from 1 to x squared, and then take the derivative. So as you know, the integral of sine is negative cosine. So we're going to evaluate it from the lower limit 1 to x squared and then take a derivative. That's what this says. So we are integrating sine t dt, evaluating it from 1 to x squared. Then we take the derivative. That's what I'm saying here. And in other words, never mind the theorem. I want to show you the theorem works here. So minus cosine t. Okay. First you differentiate. You integrate. You got minus cosine t. Now you're going to plug in. If I plug in, I can keep the negative outside here or here. I get cosine of x squared minus cosine of 1. I can keep this negative here or outside, makes no difference. Just don't lose it. Now, we are going to differentiate this. What is the derivative of cosine x squared? The derivative of cosine is negative sine. So minus sine x squared times 2x. Remember by the chain rule? What about the cosine 1? Cosine 1 is a number. Its derivative is 0. So I hope you see that. So if you look at this one, negative times negative makes it positive. Sine x squared times 2x. That's exactly what we have here. So they are the same. So I hope everybody can see that what's going on here. It's very straightforward. I wanted to show you that even if you actually work it out and then apply the derivative at the end, it works. Find the derivative of the function, okay? The derivative of plus the derivative of the integral of a to x f of t dt is simply f of x. But over here, the derivative of the integral of tan t dt as it goes from 1 to x squared plus x. First and foremost, this is your function, f of t is tan t. So according to what we have here, you are going to plug in t equals the upper limit and then times the derivative of that. So first, replace the t with the upper limit and then times the derivative of the upper limit, which is 2x plus 1. And put the 2x plus 1 in front, and you're done. What if we have an upper limit as a function of x and the lower limit as a function of x? Uh, in that case, first of all, the function is t squared. Secondly, here's the formula. The derivative of the integral of f of t dt as it goes from g to h. You plug in the upper limit f of h of x times h prime of x by the chain rule minus, now you plug in the lower limit f of g of x times its derivative again by the chain rule. So what this means is plug in sine x, you get sine squared times its derivative cosine x, sine squared times its derivative cosine x, minus plug in the lower limit, tan squared x, then times the derivative of tangent, which is secant squared. I'm just following this, and uh, it's very easy to follow. Finally, what is the derivative of the integral of 1 sine x to 1 of the integral of 1 plus square root of 1 plus t squared dt? First and foremost, here's your function. You should recognize the function. Now, we are going to interchange the upper and lower limit, and we make this a negative. Because if you look at this function, you plug in the upper limit and you multiply by g prime as long as the upper limit is a function and the lower limit is a number. And because we are interchanging those, we put a negative sign. So the answer is keep the negative, and the square root of 1 plus t squared, replace the t with sine, you get the minus the square root of 1 plus sine squared. Then you need the derivative of the top times cosine x, and then you put that in front, you get minus cosine x, the square root of 1 plus sine squared of x.